Welcome back to Science Corner. Today we're diving into the world of unmanned surface vehicles, those autonomous boats that are making a splash in fields, from oceanography to the military. They're also called USVs for short. We've got this fascinating research paper we're going to unpack, one that proposes a totally new way to control these USVs, a scheme that promises to make them even better at navigating a set course, boosting both accuracy and efficiency.
Yeah, what really caught my eye in this paper was the emphasis on something called prescribed time control. It's not just about getting the USV from point A to B.
Right.
It's about doing it within a specific time frame, a time frame set by the user.
Okay, so it's like having a delivery guarantee even out on the open ocean. Why is that so important?
Exactly. Think of a search and rescue mission where every second counts.
Oh, yeah.
This kind of control system guarantees the USV arrives on time, but it goes beyond speed. It's about reliable timing even when conditions are unpredictable. Think about ocean currents, wind gusts, even just the limitations of the USV itself. This control scheme aims to factor all that in.
So how does it actually work? The paper mentions something called disturbance observers. Do those play a role?
Absolutely. It's like having a highly skilled navigator on board who can anticipate and adjust for those unexpected bumps in the road, or rather, waves in the sea. These disturbance observers predict and counteract disturbances like wind, waves, and even those tricky modeling uncertainties that can throw a USV off course.
Ah, so it's like a built-in safety net to keep the USV on track.
That's a great way to put it. And to make it even more efficient, they've incorporated an event-triggered mechanism.
Okay.
Traditional control systems are constantly checking for errors and making tiny adjustments, which, eats up processing power and communication bandwidth.
So it's kind of exhausting, like constantly micromanaging the USV.
Precisely. This new event-triggered mechanism is more like a set-it-and-forget-it approach. The controller only kicks in when there's a significant error, saving resources and reducing wear and tear on the system.
Okay, that makes sense. So we're essentially giving the USV more autonomy, letting it do its thing until it truly needs a nudge in the right direction.
You got it. And that leads to one of the biggest advantages highlighted in the paper: efficiency. By cutting back on the constant communication, we're extending the USV's operational time and making it much more energy efficient.
Now, I know we're all science enthusiasts here, but some of this is getting pretty technical. The paper mentions a 3DOF dynamic model, transformation matrices, Coriolis forces.
Rare.
Are we going to read a physics degree to understand this?
Don't worry, we'll break it down. Essentially, they're using a mathematical model to represent the USV's movement in a simplified way. It considers things like its mass, inertia, the forces acting on it from the water and the environment. You can think of it like a virtual twin of the USV inside a computer, allowing researchers to test different control strategies.
So it's like a digital testing ground where they can fine-tune the control system and make sure it will actually work in the messy real world.
Exactly. And at the heart of this innovation is something called a prescribed time lumped disturbance observer, or PTLDO. It's responsible for observing or estimating the combined effects of all those disturbances we've been talking about.
So it's like our skilled navigator is now also a master predictor, able to anticipate the waves before they hit. And the prescribed time part means it's doing all this prediction within that strict time frame we talked about earlier.
Precisely. Remember, this observer is working in real time, constantly updating its predictions based on the USV's current state and the ever-changing environment. It's quite a feat of engineering.
Now, the paper also mentions several assumptions and lemmas. What are those, and how do they fit into this whole control scheme?
Good question. Assumptions are like the ground rules we establish before we start building the system. For example, we assume that the desired path for the USV is smooth and differentiable, meaning no sudden jumps or changes in direction. Basically, it needs to be a path the USV can actually follow realistically.
That makes sense. We can't expect it to teleport. Right. So what about these lemmas?
Lemmas are like mini theorems that help us mathematically prove the stability of the control system. They're the scaffolding that ensures the whole structure is sound and reliable.
I'm starting to get the picture. So we have these ground rules, our mathematical scaffolding, and our master predictor, all working together to create this really advanced control scheme. It's like a symphony of science.
You could say that. And the paper actually provides a detailed mathematical proof to show that this scheme guarantees stability and performance within a prescribed time. It's not just a theory, it's backed by solid math.
That's reassuring. It's one thing to have a fancy new system, but it's another to know it's been rigorously tested and proven. Now, the paper also throws around this phrase, prescribed time, prescribed performance constraints. What in the world does that mean?
It's all about setting limits, like creating a virtual corridor around the desired trajectory. We're ensuring that the USV doesn't deviate too far from its path in terms of both distance and time.
So it's like setting up guardrails for the USV, making sure it doesn't stray too far off course.
Exactly. These constraints guarantee the USV hits that desired level of accuracy even with unpredictable disturbances. It's all about efficiency, too. The USV isn't wasting time and energy correcting huge deviations.
Now, the paper dives into the specifics of how this all works, mentioning things like an auxiliary air vector and an air transformation function. Is this where we need that physics degree?
Well, those details are definitely more technical, but the core idea is that we're using math to simplify a very complex problem. Instead of directly tackling trajectory tracking with constraints, we transform it into a more straightforward problem without constraints.
So it's like finding a shortcut through a dense forest. We're using mathematical insights to make the control system's job easier and ultimately more effective.
Precisely. And this leads us to one of the most intriguing parts of this research, how they use something called Lyapunov functions to analyze the stability of the whole system.
Lyapunov functions, now that sounds intimidating. Can you give us a sneak peek at what those are all about before we wrap up part one?
Think of it this way. Lyapunov functions are like energy functions for our system. By looking at how these functions change over time, we can determine if the control system is stable and if those pesky errors will eventually disappear.
So we're checking the USV's energy levels to make sure it has enough oomph to stay on course. This is getting really interesting. I can't wait to delve deeper into these Lyapunov functions and the rest of the paper's findings in part 2 of our deep dive.
It's going to be fascinating. We'll uncover how these functions work and what they reveal about the robustness of this groundbreaking control scheme.
Welcome back to Science Corner. We're in the middle of unpacking this incredible new control scheme for USVs, and last we left off, we were about to delve into something called Lyapunov functions. You made them sound pretty mysterious.
Well, they're a powerful tool in control theory. Imagine you're trying to balance a marble at the bottom of a bowl. The marble wants to settle at the lowest point, the most stable position, right?
Right, it'll roll around a bit, but eventually it'll come to rest.
Exactly. Lyapunov functions help us analyze systems in a similar way. If we can find a function that behaves like the energy of our USV system, and that energy is always decreasing and settles at a minimum point, then we know the system is stable. It's like that marble finding its equilibrium at the bottom of the bowl.
So we're looking for a mathematical way to prove that the USV won't go spiraling off course,
Yeah,
that it'll always tend to correct itself and stay on track.
precisely. And the researchers behind this paper were clever enough to construct a Lyapunov function that captures the essence of the USV's movement and its interaction with this new control system. Through some elegant math, they demonstrate that the energy of the system, as represented by their Lyapunov function, always decreases over time, ultimately leading to a stable state.
That's really impressive. It's like they've mathematically guaranteed that the USV will behave itself, even in unpredictable conditions. But real-world engineering is rarely that simple, right? There must be some practical considerations, too.
You're absolutely right. One of the biggest challenges with any control system is dealing with the physical limitations of the hardware. The paper tackles this head-on by addressing something called actuator saturation.
Actuator saturation. That sounds intense. Break it down for us.
Think about it like this. You're pressing the gas pedal in your car. You can only press it down so far, right? At some point, you're at full throttle, and pressing it further won't make the car go any faster. That's essentially actuator saturation. The thrusters on our USV can only produce so much force.
So it's like trying to turn the volume knob past its maximum setting. You're not going to get any louder. What happens to the control system when it encounters this kind of limitation?
That's where things can get tricky. When the control system commands more force than the thrusters can deliver, it can lead to unpredictable behavior, even oscillations or instability. It's like the system is overexerting itself, pushing against its limits.
Not ideal. So how did the researchers address this problem?
They incorporated what's called an anti-windup compensator. It acts like a safety valve, adjusting the control signals to ensure they stay within the capabilities of the thrusters. It prevents that overexertion and keeps the system running smoothly.
Okay, so we've got our stability guaranteed by the Lyapunov function and our safety valve in place to prevent the system from pushing too hard. Anything else we need to worry about?
Well, there's one more theoretical hurdle they had to clear, something called xenobehavior.
Xenobehavior. Sounds philosophical. Does this involve paradoxes?
Not quite. It's a control theory term that describes a situation where the system triggers an infinite number of events in a finite amount of time. Imagine you're trying to walk to a wall by taking steps that are half the distance of your previous step. You'll keep getting closer, but never actually reach the wall because you're taking infinitely smaller steps.
Ah, so the system is stuck in a loop, constantly making adjustments, but never quite reaching stability.
Exactly. Luckily, the researchers prove that this new control scheme avoids xenobehavior. They show that there's always a minimum time interval between those control actions, preventing that infinite loop scenario and ensuring the USV actually reaches its destination.
Okay, so they've addressed stability, hardware limitations, and even those theoretical paradoxes. It sounds incredibly robust.
Mhm.
But at the end of the day, does it actually work? Does the paper include any real-world testing?
It does. They actually put this new control scheme through its paces in simulations, and the results are impressive. They tested various starting positions, introduced disturbances like wind and waves, and even simulated those actuator saturation scenarios we talked about.
So they really threw everything they could at it. How did it hold up?
Remarkably well, the USV consistently achieved accurate trajectory tracking within the prescribed time, even in those challenging conditions. Not only that, but the event-triggered mechanism significantly reduced the number of control updates needed compared to a traditional time-based system.
So it's not just more accurate and robust, it's also way more efficient, using less energy and communication bandwidth. That's a trifecta.
It really is. And to really put it to the test, they compared their event-triggered prescribed time control, or ETPTPC for short, against 3 other existing control strategies.
It's like a control system showdown. Who came out on top?
ETPTPC outperformed the competition in both accuracy and efficiency. They even compared their prescribed time-lumped disturbance observer, or PTLDO, with a couple of other types of disturbance observer.
And I bet the PTLDO came out on top too.
You guessed it. It demonstrated superior accuracy in predicting those tricky disturbances, further reinforcing its value in this control scheme.
This is really exciting stuff. It seems like they've truly pushed the boundaries of USV control with this research.
They certainly have. And it's not just theoretical. The paper's conclusion highlights the potential for this control scheme to revolutionize the field, impacting everything from autonomous navigation and ocean exploration to even more complex missions like search and rescue.
Speaking of the future, I'm curious to hear your thoughts on where this research might lead. What kind of impact do you see this having on the world of USVs?
That's a great question. I think this research opens up a world of possibilities. As USVs become more prevalent in our oceans, the demand for this level of accuracy, efficiency, and reliability will only increase.
And this paper has really laid the groundwork for meeting that demand.
Absolutely. But it's also important to remember that this is just the beginning. There are still challenges to overcome and questions to answer. For example, how can we make these systems even more adaptable to the complexities of the real world?
So it's about constantly pushing the boundaries of our understanding, refining these models and algorithms to handle those inevitable surprises the ocean throws our way.
Exactly. And another exciting avenue is exploring how this control scheme could be integrated with other emerging technologies like artificial intelligence and machine learning. Imagine USVs that can learn from their experiences, becoming even more intelligent and autonomous over time.
That's incredible to think about. We're really on the cusp of a new era in autonomous vehicles. But before we get too carried away with the future, let's take a moment to recap the key takeaways from this groundbreaking paper.
Good idea. In the final part of our deep dive, we'll distill the most important insights from this research and explore some of the exciting questions it raises for the future of USVs and the way we explore and interact with our oceans.
Welcome back to Science Corner for the final part of our deep dive. We've been on quite a journey exploring this new control scheme for USVs, and it's amazing to see how much thought and ingenuity goes into making these autonomous vessels so accurate and efficient.
It really is a testament to the power of engineering and mathematics, combining those fields to solve real-world challenges.
Absolutely. So before we wrap things up, let's take a moment to distill the key takeaways from this research paper. What are the big aha moments that our listeners should walk away with?
Well, firstly, I think this paper highlights the growing importance of something called prescribed time control for USVs. It's not just about getting from point A to point B, it's about doing so within a very precise time frame, which can be crucial for a whole range of applications, especially those time-sensitive missions we talked about.
Yeah, it's like having a guarantee that your package will arrive exactly when you need it, even if it's being delivered by a drone boat in the middle of the ocean.
Exactly.
Hmm.
The second key takeaway is the ingenious use of disturbance observers. These are like built-in navigators that can anticipate and compensate for all the things that can throw a USV off course: winds, waves, currents, even the limitations of the USV itself.
Right, it's like having a co-pilot who knows the ocean inside and out, constantly making subtle adjustments to keep the vessel on track.
And finally, I think the introduction of this event-triggered mechanism is a real game changer in terms of efficiency. By only making adjustments when absolutely necessary, the system conserves energy and communication bandwidth, allowing the USV to operate for longer and handle more complex missions.
So it's more than just a clever control scheme. It's a whole new approach to thinking about how we design and operate autonomous vehicles. It makes them smarter, more adaptable, and ultimately more useful in a wider range of scenarios.
Absolutely. And what's so exciting is that all of this is backed up by solid mathematical proofs and rigorous simulations. This isn't just a theory. It's a well-tested system that has the potential to revolutionize how we use USVs.
It's truly groundbreaking research, and as with any breakthrough, it opens up all sorts of possibilities for the future. What are some of the questions this research raises in your mind? Where do we go from here?
Well, for one, I think there's still work to be done in making these systems even more adaptable. The ocean is a complex and ever-changing environment, and there will always be unexpected challenges that our models can't fully predict.
So it's about constantly refining our understanding, improving the algorithms, and pushing the boundaries of what these systems can handle.
Precisely. And another exciting avenue is exploring how we can integrate this control scheme with other emerging technologies, like artificial intelligence and machine learning. Imagine USVs that can learn from their experiences, becoming even more autonomous and capable over time.
That's a fascinating thought. We can have USVs that not only follow a pre-programmed path, but also adapt to changing conditions, make decisions on the fly, and even learn new ways to navigate efficiently. The possibilities are endless.
They really are. And as we wrap up this deep dive, I think it's important to remember that we're just at the beginning of this journey. The future of USV technology is incredibly bright, and this research has given us a glimpse of what's possible when we combine cutting-edge science with innovative engineering.
Well said. It's been an absolute pleasure exploring this fascinating topic with you. And to our listeners, we hope you've enjoyed this deep dive into the world of advanced USV control systems. If you're eager to learn more, we encourage you to check out the original research paper for yourself.
And until next time, keep that scientific curiosity burning. We'll be back soon with another exciting deep dive into the world of science and technology right here on Science Corner.